Okay, I'm recording. So, welcome. We're starting a new chapter. And if you look up at the topic here, what does it say for our new topic?
Exponential and whatever that says functions.
Exponential and logarithmic functions. So, this has a lot to do, starting out, exponents. We're going to deal with exponents. We're going to learn some properties about exponents. And we're going to learn what they can be used in and some real-world applications or modeling problems over exponents. Okay. So, make sure you rip 7-1 out of your workbook because we're going to turn it in before you walk out of here. Okay, we're going to work them together. A couple you'll work on your own. Okay. So, logarithmic functions, they're getting you ready for calculus. So we introduced some new topics for you. And like I said, we're out of that review phase, and almost everything we do, we're always going to use some of our algebra and pre-algebra, and of course all of our basic math skills. But everything we're going to do is going to be new, because we're at that point in Algebra 2 where now we're in Algebra 2. No more Algebra 1 review. So today, our first section, 7-1, is about exploring exponential models. So when you think of a model in a thing, not a human model, but what do you think of? Do you have like models that you put together, like Legos or model cars? Some people are into putting together model cars.
Or a model on a computer.
Model airplanes. Well, what would you model on a computer?
I mean like the 3D objects.
3D objects? Yeah, that's modeling real-world applications. You know, when you're creating, let's say, a person inside a game, you can take a model, a wire mesh of a 3D object in the shape of a human and model that human for a virtual world inside a computer. So I think that's what you were talking about. And I'm going to start a video below, and I would like for you to watch this and take notes. Oh, let's see if it'll let me restart. No, let me. So watch the video and take notes.
Hello, my name is Mrs. Jenkins, and I wanted to discuss with you graphing exponential growth. Now, when we're graphing exponential growth, we're going to be looking at an exponential function. A function of the type where we have y equals a times b to the x power, where your exponent is your variable x, and it represents a real number. Now, the thing that we want to focus on here is the base, b. Because in your equation, when b is greater than 1, then b is going to represent what's called the growth factor. An equation will be one in which we can graph exponential growth when the base is greater than 1, as in our example here. Here we have a growth rate. Our base b is equal to 2, so the growth factor is 2. Now we want to go through graphing this exponential growth. The first thing that we want to do is make a table of values. I've gone ahead and picked several different values for x. -3, -2, -1, 0, 1, 2, and 3. Then we want to make a table of values and solve. What will the value of y be when x is -3? Well, substituting in -3 for x, we can solve for y. Y is going to be equal to 2 to the -3 power, which is equal to 1/8. If we substitute in a value of -2 for x, then we'll have 2 to the -2 power, which would be equal to 1/4. I want you to take a minute and complete this table. Go ahead and take each of the remaining values for x and solve for the corresponding value for y. When you've completed that task, just click continue at the bottom of the screen to check back in.
Okay, so if you're watching the video outside of school, go ahead and pause the video. And I'm going to pause this now. And everybody, I want you to finish this chart. Okay, we're going to come back. So in the third column, you should have put 2 to the negative 1, which is 1 over 2 to the first power, which is just 1/2. And then 2 to the 0 is just equal to 1. 1 would be 2 to the first power, which is 2, 2 to the second power, which is 4, and 2 to the third power, which is 8. So you should have had all these things written in, and then we're going to graph them. So I'll continue the video now.
All right, let's see the values that we should have. When x is negative 1, y is going to have a value of 1/2. When x is 0, y will be 1. When x is 1, well, 2 to the first is 2. When x is 2, we're going to have 2 squared, or 4. And when x is 3, we will have 2 to the third power, which has a value of 8. So in our table of values here, we now are going to have ordered pairs. Negative 3, 1/8. Negative 2, 1/4. Negative 1, 1/2. 0, 1. 1, 2. 2, 4. And 3, 8. So we need to graph these ordered pairs. When all of our points have been graphed, we'll connect the points with the smooth curve. I want to go ahead and do that. Looking at our first ordered pair, negative 3, 1/8. Then we have negative 2, 1/4. Negative 1, 1/2. Our y-intercept will be 0, 1. Then we have the point 1, 2. And our next point is 2, 4. The last point that we did in our table of values was the point 3, 8. You can see as you get in this example to these positive values, the value grows rapidly. Our graph shows that exponential growth, and it climbs very quickly. Now we want to go ahead and take the points that we've plotted and connect them with a smooth curve. The graph that we have drawn here will illustrate a graph of exponential growth, particularly where y is equal to 2 to the x power. Work well.
Okay, so something I want to point out real quick is that notice that they just used whole number unit measures. So from the origin down the x-axis to the right they have 1, 2, 3, 4, and to the left they have negative 1, negative 2, negative 3, negative 4, and vice versa for the y-axis. Just whole numbers. So when you end up with very small fractions, and you had 3 of those right in a row, 1/8, 1/4, and 1/2, you want to just estimate. So you know what's your halfway point? The 1/2. So that would be halfway between the 2 points. So you might want to do that one first, negative 1 and 1/2. So you would go back to negative 1 and go halfway between those two. And then you know the 2 previous ones are going to be a little less and a little less. Or you could think of it this way. You know, the 1/8, it means you're going to divide between 0 and 1 into 8 pieces. And you're going to put a dot at the first one. So truly, it's just barely over that x-axis at the negative 3. And then a quarter, that means if you were to divide that unit into 4 pieces between 0 and 1 on the y-axis, you would take the first quarter, the first fourth, at negative 2. So about right there. And then you're back to your half, and then you're at whole number increments of 0 and 1. That's your y-intercept where it's crossing the y-axis. And then we have 1 and 2 up here, 2 and 4, and 4 and 8. And notice, like she said, as you get into the positive numbers, this grows very quickly. So it can shoot off your page very quickly. So I will usually just draw an arrow showing that, well, it's up there somewhere, and do the best that I can with my graph. And we'll probably run into that today. Any questions about this? Okay. She said this was exponential growth because as it goes from left to right on the x-axis, our y values are growing. So as you move forward on the x-axis, your y values increase, and it's rising from left to right, it's rising up. The further you go to the right, the higher up it goes. So we call that an exponential increase. Okay. And we'll talk more about that in a minute. All right, so let me shrink this. Okay, so now on. I've taken a few notes here about our essential understanding. It says you can represent a repeated multiplication with the function in the form of y equals a times b to the x power, where b is a positive number other than 1. Set this familiar. This formula is going to be very familiar today. This y equals a times b to the x power. So an exponential function is a function in the general form in just that, y equals a times b to the x power, and a cannot equal 0. Well, what would happen if a was equal to 0? Let's look. If I've got this written up here, y equals a times b to the x, and they say a cannot equal 0. Well, let's just make b a value right now. Let's make b 5. So let's play like this. B is 5. Well, what happens? I've got a times b to the x. Now I'm going to say, well, a is equal to 0. Well, what happens? Whatever 5 to whatever x power you have, it's going to be some number, and we're going to multiply that times 0. So that's why they say a cannot equal 0, because it's going to turn the whole thing to 0, and you basically have nothing. Okay? So b, that's one thing we want to watch for as we work through these and make sure that we don't have a 0. The first problem is the one we just worked online, so I'm not going to do that again. Okay, notice it's the exact same problem they did on the video, except they've added one extra x value of -4 in there. Okay, so notice that it's even smaller than our -3 value. All right, and we're going to talk more about that in a few minutes too. But for right now, if there are no questions on that video, any questions? Okay, so I would like for you to work 1 and 3. Scribble out 2 and 4. I've had people all day long working 2 and 4. Don't work 2 and 4, just 1 and 3. Okay? Work those now. I'm going to give you 3 minutes. And if you are, now I'll just let it go even for those at home. If they're working and making up work, this will be good. We'll just leave it going. Do I have any seniors taking the CPR? Okay. Okay, 2 minutes. Work fast. 1 minute. Say that one more time. If you want to do a fraction, just as long as you know how to graph it, it's fine. It doesn't make any difference to me if you do a fraction or you take it to decimal. Whew. Okay. Grading papers up here as well. So let's look at the first one. And it says y equals 3 to the x power. So let's see if I can delete some of this stuff. So the y equal 3 to the x. Almost there. All right. So what you want to do is make your t-chart of x and y. So they already put the values there for x, -2, -1, 0, 1, and 2. And then on the y values, they put a middle column there for you to write in your 3 to the power. And then the right-hand column, they had y equals. And they gave you the first one, which was 0.11. All right, 0.11. Now, everything else you had to fill in. So next we have 3 to the -1, which is 1 over 3 to the first power, which is 1/3, or 0.333. Okay? So if you left it as 1/3, that's fine too. Next, you have 3 to the 0 power, which is just 1. And then you have 3 to the first power, which is 3. And then you have 3 squared, which is 9. So there's your points. Now you want to graph those. So you've got -2 and 0.11. So just over that x-axis right there at -2. The next one, -1, about 1/3 of the way up. Well, here's my halfway point I've got with the tiny little blue mark right there. That's my halfway. So 1/3 is, going to be between those two, up a little higher. 0 and 1, that's my y-intercept right there. And then 1 and 3 over 1 up 3. And then 2 and 9, which goes off my page. So it's way up there somewhere. All right, so now you want to connect everything with the smooth point. So notice that this point, and we're going to talk about this in just a second, it never hits the x-axis, it never intersects or passes the x-axis. But it gets closer and closer and closer as you go to that negative infinity. Okay, we're going to learn the term for that is called asymptote. But for right now, we're just going to know that it never crosses or touches that x-axis, and it's going to grow slow, 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 and as it goes to the right, it's going to grow very rapidly up. It would be more like that. Okay. Now I'm just freehanding that, but it's going to do something like that. Okay. Any questions? So you've got your chart, and then you did your graph, and then for 3. You would have had, and I'm just going to talk through 3, you've got your y values are going to be 3/4, 3/2, and then 3, 6, and 12. So when you plot those, again, it's going to start out very, very small at -2, and then it's going to slowly grow till you hit the y-axis, and it's going to intersect the y-axis at 3, that's your y-intercept, and then it's going to grow quickly to 6 and then 12. So it's going to shoot off the charts after that. Okay? So make sure you've got your table filled in and you've got your graph. Okay? Those are each 2 points for today's homework. Okay? Moving along. 2 types of exponential behavior are exponential growth and exponential decay. And I talked a little bit about the exponential growth in our first problem. Now we're going to talk about exponential decay as well. So growth, I'm going to highlight this in yellow as I go, is when you move from left to right and it starts out very, very low, down by the x-axis, and then it shoots up really, really fast and grows upwards as you're going from left to right. That's an exponential growth. Okay, when you start out from the left going to the right, when you start out really, really high, and I'll choose a different highlighter here, let's do the blue. When it starts out really, really high, and then it starts going downwards as you move towards the right, it's falling, right? So we call that an exponential decay. So we've got growth is where it shoots upwards, and decay is where it starts high and it falls downwards. So the formal definition here for exponential growth, as the value of x increases, the value of y increases. So as x goes up, y goes up. For exponential decay, as x increases, y decreases. See, as we go forward on x, y is falling down, 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 down. Okay? And it approaches the 0 mark. Now, I said we've got these things called asymptotes. So here's the formal definition. The exponential functions shown here are asymptotic, I hope I pronounced that right, to the x-axis. So what that means is it's going to get really, really close to the x-axis, but it's never going to intersect the x-axis. So an asymptote is a line that a graph approaches as x or y increases in absolute value. So just know it just means it's going to get really, really close to that axis. It's going to get as close as possible as you approach infinity, and we'll talk about this in tomorrow's lesson. But it's never going to touch that x-axis or the axis that it's asymptotic to, which here it's the x. See, it gets really, really close, but it's never going to touch. So that's an asymptote. So it says the x-axis is an asymptote, right? Because the graphs get really close, but they never touch. All right. Any questions on asymptote? We'll use that a lot this chapter, by the way. Now, I really marked this up last hour, so let's delete some of this. I'll leave it. Okay, so now here's our formal concept summary about exponential functions. So for the function y equals a times b to the x power, if a is greater than 0 and b is greater than 1, then the function represents exponential growth. So truly, if I had an equation like y equals 3 times 5 to the x power, so 3 is my a, right? So what's my b? 5. So it says if a is greater than 0, is my a greater than 0 here? Yes, because it's 3. And now let's check. Is b greater than 1? Then I've got exponential growth. Done. Okay? Easy, right? Now let's look about decay. I should have grouped this other stuff first. All right. Now, if a is greater than 0, both of them say that, right? So that's true for both of them. A must be greater than 0, so we need a positive a. It can be a fraction. It could be positive 0.25, right? But it can't be negative anything, and it can't be 0. So if it's positive, if a is positive, and b is between 0 and 1, then you've got exponential decay. So let's think of an example that might represent that. So let's pick an a value that's greater than 0. Somebody give me a value. I heard 4 first, and then I heard 5. So I'll use 5 for my b value. So but wait. 5 would mean we've got a growth, right? let's pick a b value that creates a decay. So it's got to be between 0 and 1.
How about a fifth?
Say again?
A fifth?
1/5, okay? Which is 0.2 to the x power. So we could write it as 1/5, or we could write it as y equals 4 times 0.2 to the x power. So because my a value is positive, and my b value is between 0 and 1, I have exponential decay. That's all there is to that. Any questions? All right, look at your next set of problems. Look at number 5. Wait, let me make sure there's nothing else I need to show you. Oh, one other thing I need to point out before we do this. In either of these cases, whether you've got growth or decay, you've got a y-intercept that's 0, a. So your a value is always going to be that y-intercept. So here for your y equals 4 times 0.2x, my a value is 4. So the intercept to this would be 0, 4. Pretty easy stuff. So let's apply all this to the first problem. So write your formula down. Start out by writing your formula. Y equals a times b to the x power. All right, now let's apply. So we've got, what's our a value in number 5? And for those at home, y is 3 times 7 to the x power. So what's my a value? 3. What's my b value? 7. So a is positive, so we're good there. And my b is it greater than 0, or is it between 0 and 1? It's greater than 0, so that means it is a growth. So you're going to write exponential growth there for number 5. That's all they're asking. Is it growth or decay? So that's a growth. Now let's look at 6. So we have y equal 4 times 2.5 to the x power. So my a is positive, and my b is 2.5. Is that a growth or decay? 2.5. So you have to decide, is this between 0 and 1, or is it greater than 1?
It's a growth.
Because
Because it's greater than 1.
because it's greater than 1. It's greater than 1, so it's an exponential growth. So if you want to abbreviate and just do like EXP growth, that's fine. You don't have to spell it exponential.
And just put growth or decay there.
Yeah, but just realize that the whole term, the true term, this is all about exponential growth and exponential decay. So don't forget about the term. All right. So now what about 7? Do I have growth or decay? I have decay. So write exponential decay. And then work 8, 9, and 10. And I'll talk about 10 in just a second if you don't see the trick on 10. Okay, so look up here, number 10. What is my a value?
Your a value should be 1.
Absolutely 1, because this has to be my b value because it's with the exponent. So that has to be my b. That means that there's that pesky little 1 that we leave off so often, right? So if I ask you to tell me what is the y-intercept for this, what would you say? Remember, it's 0, a.
The y-intercept would be 1.
And then how would we write it in coordinate form?
It would be 0, 1.
Yes. Okay, everybody see that? So now, applying that, I would like for you to work 11, 12, and 13. You're just telling what the y-intercept are to each one of those problems. So it's always going to be the 0, comma, a, whatever your a value is. So for 11, you've got y equals 2 times 0.75 to the x power. So we know it's 0, comma, a. And here my a is a 2. So my y-intercept is what? 0, comma, 2. So that's your answer for number 11. Now quickly, about 5 more seconds, do 12 and 13. Those are quick, quick, quick. And 13, you're going to do the same trick as you did in 10 about applying the 1. Okay, moving along quickly here. It says identify exponential growth and decay. So problem 2 says identify each function or situation as an example of exponential growth or decay. What is the y-intercept? So we've already done this. This is just like the previous problems that we did of 5 through 7, or 5 through 10, excuse me. So we're good there. Now let's do a model with this, okay? Let's determine how do we apply this exponential growth and decay into a real world situation. So they say you put $1,000 into a college savings account for 4 years. Okay. The account pays 5% interest annually. So they want to know the amount of money in the bank is growing by 5% annually. So we have, is our account growing or shrinking? It's growing. So that's an exponential growth because your 5% every year is going to be 5% more every year. So it's going to grow every single year, get larger. So this represents exponential growth. The y-intercept is 1,000 because remember when we used to do the fallen object models, or I always talk about, okay, this is your beginning point, that becomes your y-intercept. That's where you always start, is that y-intercept. So if they're starting with $1,000, that's your y-intercept, 0, 1,000. Talking about money. We're starting here. So that's your y-intercept. Where are you starting from? Now, if we think about the 5% and the 4 years, that means we've got something timed. We've got $1,000 initially. We've got something about time, and it's growing at 5%. So let's look. What were they asking us? Oh, they want to know what's the y-intercept. Is it growth or decay? We've already covered that. It's growth. And then that 1,000, this is preparing us for our next set of problems, by the way. That 1,000 is our y-intercept. So if that's our y-intercept, what part of this equation is this going to be? A or B? It's going to be our A because A is our intercept, right? So when they tell you you're starting with this much money, that's your A value. That's what's going to go there. All right? And we're going to learn more about this in just a second. So the answer was growth and 0, 1,000. Now you've done 5 through 13. Now moving on. So for exponential growth, we've got y equals a times b to the x power, where b is greater than 1. If b is greater than 1, then we say that b is the growth factor. That's the factor at which it's growing. So that 5%, that would be your b. 0.05, excuse me. A quantity that exhibits exponential growth increases by a constant percentage each time period. The percentage increase, R, is written as a decimal, and it is the rate of increase, or the growth rate. So for exponential growth, we're going to have B equal 1 plus R. Okay, B equal 1 plus R. For decay, your B is going to be between 0 and 1. Okay, then it would be the decay factor. So if you add a rate, let's say if you're growing at 5%, you're going to have B equals 1 plus 0.05. So B is going to equal 1.05. That's greater than 1, so you've got a growth. Well, what if your growth rate is a negative number? Let's say it's negative 0.05. So when you take away 0.05 from 1, you've got something less than 1, which means now that B less than 1 is going to be a decay factor. So let's look at how to use these. Let's see. The percentage decrease is R. That would be called your rate of decay. So if you've got a growth, it's a growth rate or rate of increase. If you've got a decay, the R value becomes rate of decay or the percentage decrease. All right. So what we're going to do, turn to 14, 15, and 16, and let's do these together quickly. It's actually a lot easier than this seems. Okay. Just write down above your first problem, or right above your instruction, write B equal 1 plus R. So for 14, they say for each annual rate of change, find the corresponding growth or decay factor. So 14, we have 35%. So they said put it in a decimal form. So we have to do it as, remember how to take the percentage sign off? Take your decimal back to the left 2 places. So that gives us 0.35. So 35% is equal to 0.35. So that's our R. So now B is equal to 1 plus R, or in this example, 1 plus 0.35. That's going to be equal to 1.35, which is larger than 1, so we've got a growth factor of 1.35. Easy, right? Now for 15, they give us negative 20%. So turn it to a decimal. That would be negative 0.20. And now add that to your equation. B equal 1 plus negative 0.2. So that's going to give us 0.8, which is between 0 and 1. So what is that going to be? An increase, or a growth, or a decay? Because when you take 1.00 and you subtract 0.20, you get 0.80. You're welcome. So that takes us between 0 and 1, so it's a decay factor. All right. Now look at 16. We've got 62%. So what are we going to have? A growth or a decay?
62% is going to be growth.
Mm-hmm. So B is going to be equal to what? 1.62. Yes, because you have B equal 1 plus R. R is 0.62. So it's 1.62 greater than 1, so it's a growth. All right, now let's look at the next problem quickly. Now it says you can model an exponential growth or decay with this function. So here's the big problem right here in the middle. and I wrote it a little bigger in blue right there. So it's A, capital A of t equals lowercase a times 1 plus r, there's the thing we were just working with, the growth or decay, to the t power. Now, I want you to fill in these blanks on 17. A is, the lowercase a is equal to what? The initial amount. So write initial amount there. On number B, it says R is equal to, well look, R is your rate of growth or decay. Rate of growth or decay. And T is the number of time periods. Okay? So that's this formula. Now we're going to apply it to the last problem. I told you it'd be done today. So, thank you. Thank you. That's all. Okay, so we've got our last problem here on number 18, excuse me. So we're going to use this formula over, this is the major formula for exponential growth and decay. Capital A, and the capital A means how much do you have after your time period? The A of t, that means what's your final amount after the time passes. So that's going to be like your y equals, but we have A of t equals. Now lowercase a is different than the uppercase a. Right, so lowercase a is your initial amount, what did you start with, times 1 plus r, the thing we just did in the last problem set about rate of growth or decay, and t is your time period. So let's look at, actually I won't even do the example, let's do the one in the book. Okay, so in your example here, notice that in 17 the formula is still written there, so use that. A of t is equal to lowercase times 1 plus r to the t power. Alright, so it says the population of Bainesville is 2,000. The population is supposed to grow by 10% each year for the next 5 years. How many people will there be in 5 years? So what's our t factor? 5, because that's how many time in years we're talking about. What's our initial amount? What did they start with? 2,000. Now 1 plus, and how much are they growing? 10%. So that's going to be 0.10. And the t again, same t is, what's our time? 5. Okay, so now when we do this, what's 1 plus 0.10? It's going to be 1.10, right? So what you want to do first in your calculator is take 1.10 to the 5th power. Do that first. And then multiply that answer times 2,000. And then write your answer. Box it, and you're done. Okay, and then we'll pass them forward in about another 90 seconds. Okay, and then no homework tonight, and make sure you've got your workbook every day, because we won't finish in class every day, but you'll get a start on each problem set. I'll teach, we'll do together, then you work a couple. If you don't finish, you take it home. But some days I'll go ahead and turn it in. Today we're turning in. All right, when you finish, pass them forward, and thank you very much. This concludes our lesson. Thank you.